we can use the technique in the last problem to do something that sometimes turns out to be kind of useful, which is to write the integral of one power of a function in terms of the integral of a lower power of that function. Taken to its logical extreme, what we can do is we can just keep doing this, keep reducing the power of the function until we eventually get a very simple expression. But just as an exercise, it's useful to be able to write the integral of one power in terms of the integral of a lower power. So that's what we're going to do here. We're going to write the integral of sine to the 17th x in terms of sine to the 15th of x, of the integral of sine to the 15th of x. Let me show you how to do that. So what we're going to do is we're going to start with a choice of u and v. The first thing is recall that the important principle of of choosing dv, which is that we want dv to be something that's going to be fairly easy to integrate. So what should we choose dv to be, looking at the expression sine to the 17th x dx? If you guessed dx, you could certainly be forgiven for that choice, but it's actually going to turn out that a better choice is sine x dx. I know you don't see a sine x in there, but remember that sine 17th is just going to be sine x multiplied by itself 17 times. So all that's going to be left over is sine to the 16th x, like that. Okay, so now we can find du, which is just going to be the derivative of sine to the 16th. That's going to be 16 sine to the 15th x, and then by the chain rule times cosine x dx. And v is the antiderivative of sine x is just negative cosine x. So there's our u and v. Okay, so let's write out what we have here. We're going to write the integral of, right up here, the integral of sine to the 17th x dx is equal to uv, so it's going to be negative sine to the 16th x cosine x, and then we have v and du. Notice that v is itself negative, so when we subtract v du, it's like we're going to be adding just without that minus sign, so that's going to be plus. Let's put the 16th outside of the integral, 16 outside the integral, and we've got sine to the 15th x, and then we have cosine times cosine, which is cosine squared x, and then finally we have that dx at the end. So we now have negative sine to the 16th x cosine x plus 16 sine to the 15th cosine squared. Now, focus on the cosine squared. I think I've mentioned this earlier in earlier lectures. What should you be thinking of whenever you see a cosine squared in this course? If you said cosine squared x plus sine squared x equals 1, and its rearrangement cosine squared x equals 1 minus sine squared x, you would be correct. That is that identity is one of the most important algebraic transformations that you have to know for this course and at least the next one. You should always be thinking that whenever you see cosine squared. There are a couple of other things we can do with cosine squared, but that should certainly be at the forefront of your mind. Okay, so what we're going to do is we're going to replace cosine squared with 1 minus sine squared. So let's just write that out. Sine to the 17th x dx equals negative sine to the 16th x cosine x plus 16 integral of sine to the 15th x 1 minus sine squared x dx. We want to do one more simplification before we go on. That's going to be negative sine to the 16th x cosine x plus 16 integral of sine to the 15th times 1 is just sine to the 15th minus sine to the 15th times sine squared is sine to the 17th x. And now we'll pull that last integral apart, so that gives us sine 16th x cosine x plus 16 integral of sine to the 15th x minus 16 integral of sine to the 17th x. Oops, sorry, I forgot to write the dx. dx is very important. As you can see, the dx has a meaning here, and you can't forget it when you do that. I just did, I know, but I went and fixed it. So this last thing becomes sine to the 17th x dx. So now look what we have here. I'll just bring this down. We simply have two different multiples of integral of sine to the 17th x dx on either side of the equation. So what can we do with that? Well, we can add 16 integral of sine to the 17th x dx to both sides of the equation. Let's do that. And I have one copy of sine to the 17th x dx already on the left side. I'm going to add 16 more copies of that, giving me 17 integral of sine to the 17th x dx equals what we have left over on the right side. Now, recall what the original problem was, looking blue up here. The problem was to write sine 17th x in terms of sine to the 15th x. We're almost there. We know what 17 times the integral of sine to the 17th x dx is in terms of sine to the 15th. All we have to do is divide both sides of the equation by 17, giving us the integral of sine to the 17th x dx is equal to negative 1 over 17 sine to the 16th x cosine x plus 16 over 17 integral of sine to the 15th x dx. And that is the answer. As I'm putting a box around this, by the way, some of you may have noticed that I left the plus c off. We don't actually need a plus c because we already have here an indefinite integral at the end, which implicitly refers to all possible antiderivatives of the expression that follows it. In other words, it carries with it its own plus c. It's only when we simplify it to a closed expression that has no integral that we need to write the plus c to represent the possibility that we could shift the antiderivative up or down by any constant. This notation here that you see at the end already encompasses that idea, so we don't actually need another plus c to be correct. Arguably, it's overkill. I know some of you are going to ask, well, can I just write the plus c? To me, that's kind of a way of saying, can I not think about what it means? So I'm telling you what it means, and the answer is it is more correct to write it. It is more correct to write it with no plus c in this case. And if you're asking for permission to not think about what that means, permission is not granted. Now I know that some of you are going to ask, is this something like this? Is this a reasonable exam problem? You bet it is.